Okay, well, it's a pleasure to be here. Thank you to everyone involved in organizing this workshop. So I'm going to be focusing in this talk on a question that's really sort of been the focus of my research over the last few years, and that's whether we can actually compute spectral properties of infinite dimensional Koopman operators. So the emphasis here is controlling the errors when we go from something infinite dimensional to a finite dimensional projection. This is based on a bunch of papers I thought I'd list at the start. So I will put these slides up on my website afterwards as well in case you need any of the references. So the first paper is really about controlling projection errors in L2 spaces. I'm going to talk about measure-preserving systems as well, and also computing generalized eigenfunctions over the continuous spectrum. And then there's a recent review paper that looks at all of these sort of the zoo or multiverse of DMD methods from a spectral theory point of view. Okay, so the setup. I don't really need to dwell on this beyond mentioning function space. So I have a state X inside some state space omega. Okay, omega does not need to be an attractor in this talk. It's just some set. And I have an unknown function f that governs the dynamics of discrete time, state of time n plus 1 as f of state of time n. And the Koopman operator, I don't need to give you the definition in this conference, but the important thing is I'm going to look at the function space of L2 functions with respect to small omega, some positive measure. Need not be finite. Okay, so it could be Lebesgue measure on something non-compact. And then this is going to have an associated inner product. And my goal is to compute spectral properties of this Koopman operator from snapshot data. So that's a bunch of points, x and y, where y is one time step forward. And at this point, I'm not specifying whether this is from a single long trajectory or multiple shorter trajectories. So that's really wrapped up in the convergence of quadrature rules, which I'm only going to briefly touch on. So for now, there are no assumptions on the snapshots omega f or small omega, other than the fact that f is non-singular with respect to omega, so you can make sense of going from pointwise to L2, and also that k is a closed operator, and it could be unbounded as well. Okay, so a bit of a warm-up, a bit of a fun slide as well. Bad things can happen even for measure-preserving systems. So let's take the bilateral shift operator on L2Z. This is a very nice operator. It's unitary. Its spectrum is the unit circle. The spectrum is stable. It's a normal operator. It has continuous spectra, so no normalizable eigenfunctions, and it corresponds to unitary evolution. Now, if we take a method such as EDMD, which is essentially a Galerkin approximation of this operator, in the large data limit, what we're doing, if we choose a natural basis for this operator, we're truncating to a finite matrix. In this case, a Jordan block. Okay, and a Jordan block is sort of the bad guy of spectral computations. Its spectrum is 0, okay, so completely wrong. Spectrum is severely unstable, in fact, exponentially so as you increase the truncation parameter. It's got discrete spectra, and you get nilpotent evolution. Okay, so this is obviously a very simple example, but it captures the essence of what can go wrong with DMD methods if you try and approximate spectral properties of Koopman operators. So in fact, lots of dynamical systems can be built up from operators like this. Okay, so when we truncate or discretize to a matrix and compute eigenvalues, which is probably the predominant method for approximating spectra, there are dangers that we have to be aware of. Okay, so first we can have too much, so that's spectral pollution or spurious eigenvalues that have nothing to do with the true spectrum, even as we increase the discretization size. We can miss regions of spectra. How do we also capture continuous spectra? Okay, so we've been seeing again and again in these Koopman mode decompositions that often capturing the continuous spectrum is essential for getting the correct dynamics. Can we verify that the algorithm's output is usable, is safe, right? So can we control the projection error or the subspace that we're projecting on? And also instability. So even if you have a nice, in this case, normal Koopman operator, okay, you can truncate and end up with a horrible non-normal matrix as well. Okay, so methods like EDMD do not avoid these dangers in general, even as you increase the size of the dictionary and your subspace becomes dense in the space you're working in. Okay, so with that in mind, I'm going to first talk about general systems and an algorithm called residual dynamic mode decomposition. I'm then going to shift gears and assume that the system is measure preserving and discuss two algorithms, rigged dynamic mode decomposition and measure preserving extended dynamic mode decomposition. Now, the thing to look out for in both of these sections is that I'm going to give you conversion algorithms, but they rely on taking multiple successive limits to infinity. So that sounds curious, but we're then going to tie this up in something called the solvability complexity index, which is a way to classify problems and prove optimality of algorithms. So this is hot off the press. This is joint work with Igor as well. And then I'll end with some open questions. Okay, so let's look at the general case first. So here's EDMD in one slide. What do? We take some functions, basis functions or a dictionary. Remember, we only have access to data, x and y. So I'm going to treat these x points as quadrature points for certain integrals. In particular, I'm interested in two types of inner products. The inner products between the basis functions themselves and with an extra k on the left here. So if I approximate this using these quadrature points with quadrature weights, Wm, I get this approximation here, which I can rewrite in matrix notation. So apologies, when I shifted the computer, some of these lines got shifted as well, but this is psi x. So this is the dictionary evaluated at the x points. Okay, so for example, if you're if your system is ergodic and you're doing ergodic sampling along a single trajectory, these Wms would be 1 over m. Or if you have multiple shorter trajectories, then you might have a different quadrature rule, which can be beneficial in certain situations. Now, to get this other inner product here, we need to replace this by the composition of psi k with the unknown f. Fortunately, we have the y points. Okay, so now we have quadrature points here for this composition, this green. Okay, so what does EDMD do? It builds a Galerkin approximation by taking the inverse of this matrix applied to this matrix here. So in other words, it's a projection of your infinite dimensional Koopman operator to a finite dimensional space corresponding to the linear span of these basis functions. But of course, I just showed you the example with the shift operator. You have to be cautious. Okay, so if we actually want convergence to the spectral properties of the Koopman operator, not only that, convergence, Koopman mode decomposition and forecasts and things like that, we have to be careful. Okay, so let's look at these two matrices again. So we've got the Gram matrix. So that's this G. We've got Koopman on the left here. So we've actually got a blue-blue matrix, a blue-green matrix. We can take the adjoint and we get a green-blue matrix. And at this point, I often ask people, what's the missing matrix? Any guesses? If you're just going via the color scheme. No one's going to... Green, exactly. So what does green correspond to? It corresponds to having an extra k here on the right-hand side. So I'm going to call this k2. And of course, you get this for free from the data. Okay, so I'm not using any more assumptions on my data acquisition. Why on earth would I consider such a thing? Well, I can start to compute residuals, or in other words, bound projection errors. So for example, if G is expanded in my basis functions like this, and we think it's close to being an eigenfunction, or it's an approximate eigenfunction of k with parameter lambda, I can re-express this squared residual in terms of this inner product here. Okay, so far so good. Now I can expand in terms of my basis functions. And it turns out that I can represent this exactly in the large data limit using these three matrices. So you've got this extra k2 here. Okay, so this is exact in the large data limit. Okay, no projection error here. I'm controlling, or rather computing, the projection error. So I can access infinite dimensional residuals using this extra green-green matrix. And that's the essential idea of ResDMD. So you can download the code here. You can look in the paper for algorithms. They're very easy to use and to use in conjunction with EDMD. I'm just going to give you a very brief overview of what you can do. So for example, if the quadrature rule converges, so if our approximations of those inner products converge, as we collect more and more data, we can do the following. So we can avoid spurious eigenvalues or spectral pollution as we take m to infinity. Okay, so we can clean out the garbage essentially from that projection. We can also, in two limits, as we then take the size of our dictionary to infinity, compute pseudospectra. Okay, now I'm assuming here that some sort of density of my space as n goes to infinity, but again, technical details are in the paper. So pseudospectra are these union of spectra of perturbed operators. They give us sort of a stability estimate of the spectrum. And by taking epsilon to 0, I can then compute the spectrum. So notice here I've got an algorithm, one limit, two successive limits, and three successive limits. So keep that in your mind as we get to the end of the talk. Okay, so you can also do a bunch of other things like verify dictionaries, approximate eigenfunctions, coherency, error bounds of forecasts. And you can even extend it to stochastic systems as well, where there's an interesting interpretation of residuals in terms of variances. And there's actually a residual variance decomposition. Okay, so very quickly, here are some examples of this in action. So this is a high Reynolds number flow. Okay, the ambient dimension is 300,000, corresponding to measurement points of the pressure field. We have a periodic cascade of airfoils, an inlet and an outlet here. Okay, and here I'm plotting Koopman modes, in this case using a nonlinear dictionary. I think it was with a Gaussian kernel, still working in a Hilbert space. And here are the relative errors that you compute using the residuals. So you can get verified Koopman modes, verified spectra of these systems. Please don't ask me what the physical interpretations of these are. I wouldn't know. That's down to my collaborators. Okay, right. Verified spectra modes. We can also verify dictionaries. So here I've got a turbulent flow pre-transient, okay? And I have two dictionaries, a linear dictionary and a non-linear dictionary, and I'm associating residuals with the eigenvalues computed using EDMD. Okay, so a blue here means a small residual and is good. Okay, so you can kind of compare this sort of fingerprint for the two dictionaries, and you know that the nonlinear dictionary is capturing sort of invariant subspaces to a better degree than the linear dictionary. And then you can actually compute these modes again. I think this is some point around there. Also, the point is these are not close to 1. Okay, you can also do verified KMD and compression. So here we have a very nonlinear shock wave produced by a laser cannon. So here's the laser cannon in action. Fortunately, he wasn't in the path of the laser cannon. But there's a shock wave we want to capture. So we trained the model and then we tested it on unseen shock waves. And what I'm showing you is what happens when I do a prediction based on faulty modes. So in red we have what happens when you keep the dominant modes according to the SVD. Okay, so that's what we would naturally do with POD or something like that. In black is what happens when I keep the modes with the smallest residual of 40 modes. So I get a much better approximation of my wave, essentially because I'm getting rid of spurious eigenvalues or spurious modes. Okay, and then you see this much better compression of the system. And this is because, you know, for this particular example, it's very hard to capture it with a linear model. Okay, so that's ResDMD. I'm going to link this to other methods at the end and also give you some open problems. But now we're going to move to measure preserving systems. So previously I hadn't made any assumption on whether the system preserved a measure. So what is a measure preserving system? It means that this f, this unknown function that governs the dynamics, preserves the measure omega. And this is equivalent to the Koopman operator being an isometry. Okay, so the norm of k of g, for any g in our space of observables, our L2 space, that's equal to the norm of g. Okay? This is equivalent to k star k being the identity, which is not equivalent to k being unitary. Okay, so in infinite dimensions you can have an isometry that's not unitary, but we can get around that using unitary extensions, for those of you who care about such things. Okay, so we have this unitary operator. Its spectrum is is contained in the unit circle here, but the problem is that often k doesn't have a basis of eigenfunctions. So we saw that for the shift operator, and you don't have things like spectral gaps, right? So you don't know what are the dominant eigenfunctions even if they did exist. Okay, so instead, what I'm going to do is use something called Gelfand's theorem. To understand Gelfand's theorem, let's first look at the finite dimensional case. So if we have a finite n by n normal matrix B, so it commutes with its adjoint, it has an orthonormal basis of eigenvectors, these Vj's. Okay, that means that any V inside your vector space can be expanded in terms of these eigenfunctions. So you've got these projections here. Once you've got this eigendecomposition, the application of B is trivial, right? Because you just multiply by the corresponding eigenvalue. Now in infinite dimensions, we have a unitary K, typically no basis of eigenfunctions. So whenever we have continuous spectrum, there's no basis of eigenfunctions. Under some technical assumptions that you can always realize, for example, using delay embedding, so I can talk about the explicit construction if people are interested, you can replace this expansion by essentially using Gelfand's theorem, an expansion in generalized eigenfunctions. So what do I mean by that? So for G inside some test space, S of functions, okay, you can expand G, replace this sum by an integral, replace these projections here by Koopman modes, replace these eigenvectors by generalized eigenfunctions. Now these live in the dual of S star, sorry, the dual of S, so S star, which is larger than L2, okay, so they're distributions. These shouldn't be confused with the terminology generalized eigenvectors associated with chains of Jordan normal form. But anyway, so you have this expansion, you have this measure here which in effect tells you how to deal with the point and continuous spectrum on equal footing. And once you've got this expansion, you can multiply through by K. Okay, so I'm working along the periodic interval, parameterizing the circle by angle coordinates. So I get a multiplication by e to the I theta here, or lambda. And this is just another way of writing down the Koopman mode decomposition in the language of the nuclear spectral theorem. Okay, so you have an integral, Koopman modes, generalized eigenfunctions. For those of you from a physics background, this is very similar to Dirac-Braquet notation. And in fact, most of the literature on these generalized eigenfunction expansions is for Schrödinger operators. Right, so how do we actually compute this thing? It's, we've got some nasty distributions floating around, we've got a continuum of spectra. We're going to smooth everything. So I'm going to introduce something called the Carathéodory function. If you've got a background in orthogonal polynomials on the unit circle, this is a very natural object. So it's this KD-type transform of the Koopman operator applied to G, so I'll call this f of G. So it's the same expansion of G we had before, so here, except now I've got this additional scalar coming from essentially the functional calculus. What do? I pick an R greater than 1, so 1 plus epsilon, so just outside the disk, any theta naught, and I evaluate the Carathéodory function just inside the disk, subtract just outside. Lo and behold, we get a convolution of this expansion with a kernel. Turns out this is the Poisson kernel for the disk. Okay, so this is a smoothed generalized eigenfunction, and we can prove all sorts of convergence results as epsilon goes to 0. So here's the picture. So you pinch, so you evaluate just inside, subtract just outside. These guys get closer to the desired spectral parameter. As they do, this kernel becomes more and more localized around theta naught, and this gives you a sharper approximation of your generalized eigenfunction. So we're cutting up the continuous spectrum. And you can actually apply this to other things. For example, if you want to compute the indicator of a Koopman operator over a region of the Koopman spectrum as well. But here I'm just doing a peek. All right. The Poisson kernel is actually a rubbish kernel. It only converges order 1 in the smoothing parameter epsilon. The problem is, smaller epsilon actually requires more data. As we get closer to the unit circle, we need a larger dictionary size to approximate the resolvent. Larger dictionary typically requires more data for the quadrature rule to converge. Fortunately, we can construct much better kernels, so here they are. For any algebraic order M, so you get fast convergence for the generalized eigenfunctions in the topology of S star, so you can be very precise about that. spectral measures, so these are just traces of generalized eigenfunctions, so we've seen them a couple of times today. We can get them in pointwise LP sense. And forecasting, which is essentially just the functional calculus of the Koopman operator, and we can prove convergence. All right, so the final ingredient, we need to compute the resolvent, to compute the Carathéodory function, to compute the smooth generalized eigenfunctions. Let's go back to my favorite example, the shift operator. If we use EDMD, it doesn't work. Okay, so we have this Jordan block as before. If we take a Z inside the unit disk, okay, so remember the spectrum is the circle, and we need to pinch just inside and outside. This approximation diverges exponentially as n goes to infinity. Fortunately, there's a way around it. There's an algorithm called MPEDMD, so that's one of the algorithms I mentioned at the start. This essentially computes the unitary part of a polar decomposition of EDMD. For this example, you replace a Jordan block by a circuit matrix, all your troubles go away, everything converges. So for general measure-preserving systems, so for general K, this resolvent converges in a strong sense to the true resolvent. Hence, rigged DMD converges. It might look like, again, remember the number of limits. We have 3 limits, but in fact, res DMD allows us to choose the smoothing parameter adaptively on the truncation size. But that's another story. Okay, so you get convergence in 2 limits. So very quickly, here's an example for the Lorentz. Here we have purely continuous spectrum because I've subtracted the mean of the observable. I'm building my approximation space using a Krylov subspace or delay embedding. Okay, so this is continuous measure, smoothing parameter 0.05. Here are the smooth generalized eigenfunctions. They have very nice coherency properties as well, and you can actually measure how coherent they are using ResDMD again. Okay, you can do this for more realistic systems. So here's an example with a large state space dimension. We've added 20% Gaussian noise, so I don't really have time to go through all of these different settings, but it's cavity flow. Okay, and I'm going to focus here on the high Reynolds number regime where we have continuous spectra. So here's the noise-free approximations of the generalized Koopman modes deep in the continuous spectrum, and here's the reconstruction when we even add noise to the data. So it works well in practice. And you should compare this picture and also these pictures here. These kinds of structures have appeared before in Koopman papers as well. Right, so just to tie everything up at the end, so I'm now going to talk about the solvability complexity index. And what I really want to do is introduce to you how this can be a tool for classifying how difficult Koopman problems or computational problems are and whether our algorithms are optimal. Okay, so this framework extends beyond just computing spectra, as I've shown before. Okay, so let's look again at ResDMD. So we had convergence in 2 limits for the pseudo spectrum, an additional epsilon down to 0 here for the spectrum, so 3 limits if you want the spectrum. RigDMD, again, 2 limits. You have convergence in multiple successive limits, and we've seen this in various algorithms today, that you have to take certain parameters to infinity in an order, and the order matters, okay, so they don't commute. So in Julia's talk, we had a very nice example where you could combine these 2 limits and choose, in that case, m dependent on n. But in general, that's very hard, and in fact impossible. So unless you have very strong assumptions on your dynamical system, for example, uniform ergodicity or a finite dimensional invariant subspace or control on the properties of F, every convergent Koopman algorithm to date needs multiple limits. Okay? So this comes from spending the last however many months trying to trawl through and find an example that doesn't. But they all depend on these. If they don't, they all depend on strong assumptions. And these limits can be different things. Okay? So it might not just be data and dictionary size. You could have a completely different algorithm that's not based on DMD or eigenvalues. Okay, so the solvability complexity index, in a nutshell, is the smallest number k for which we can solve the problem with k limits via an algorithm. And these limits can be anything. Okay, so it's not just data, truncation size. This is sort of an abstract idea. If you want sort of an overview of this, this hierarchy, okay, you can look at this archive paper. We've also applied it to training neural networks, where we prove a distinct difference between trainability and existence. But really, sort of, it came from studying infinite dimensional spectral problems. And it allows you to classify problems and prove optimality of algorithms, very much sort of in the school of David Hilbert on the foundations of computation, but also Steve Smale. So Steve, in the 80s, initiated a program in numerical analysis on, what could you really do with algorithms? And he has a very nice paper, well, he had a very nice problem for computing the zeros of polynomials, which was then solved later on, where you see this explicit need for multiple limits, but more on that if people are interested. Okay, so here's just a big sort of picture of the SCI hierarchy for a completely different field. So this is not Koopman. So this is for computing spectral properties of operators on L2n. So L2n is the canonical separable Hilbert space. So over here we have problems that can be solved with error control. So I only talked about limits, but they're behind the hierarchy. And you get different versions of error control. So certain quasi-periodic 1D Schrodinger operators. Here are compact operators. You need one limit, but you can't get error control, which people might find surprising, even if it's self-adjoint. Over here, you need two limits, so sparse operators, normal operators. Over here are the really bad ones, three limits, general operators. And it has a calculus, okay? So I can combine sparse and normal, take their intersection, and I hop down here. So that's how that was an algorithm that I developed in my thesis for computing spectra with error control, was by studying this sort of structure. But anyway, so we have classifications for a whole zoo of spectral problems. A whole different load of people have contributed to this. And what I'd be really interested in is transferring all of these techniques across to Koopman. Okay, so joint work with Igor, we're now starting to do this to try and classify how difficult these problems are for general systems, for computing the spectrum, for measure-preserving systems, computing the spectrum, distinguishing the spectral type. That's a very difficult problem. Bottom line, so the paper will be out soon, so I can't really give too much away. But many problems are impossible to solve in one limit, even with perfect and unlimited snapshots. So I mean, you can take M as large as you want to any accuracy you want, so the noise is as small as you want, even with smooth F on compact manifolds. So for example, computing the spectrum as a set of smooth measure-preserving systems on the unit disk, where the measure, so the L2 spaces with respect to the Lebesgue measure, that's impossible in one limit. Okay, and you can prove that. That's a rigorous mathematical theorem. But many of these problems can be tackled in multiple limits under very generic conditions. Okay, so you get a new sort of program on the classification of Koopman problems. Okay, so to wrap up, as we've seen time and time again, infinities matter. Okay, so a complete picture, I think it's fair to say, has emerged on L2 spaces. Okay, so for general systems, you can compute spectral properties with error control and avoid all of those dangers if you control infinite dimensional residuals with that very simple green-green trick. Measure-preserving systems, you can deal with continuous spectra, so spectral measures, which I didn't really talk about, but also generalized eigenfunctions using smoothing and the resolvers. Okay, this, by the way, is a very classical idea, for example, in condensed matter physics when people are computing spectral measures of Schrodinger operators. Okay, convergent algorithms provably must use successive limits if you're going for generic cases. Okay? The SCI hierarchy allows you to classify problems and prove optimality of algorithms. Okay? So to end with some sort of open problems where I'd be very interested to chat with people. Other uses of residuals in res DMD. So control. So we had a discussion earlier on about controlling the projection error for control problems. What about combining it with analytic DMD, so the work of Alex and Igor, for different function spaces other than the L2 space? Okay, so what about other function spaces? What further classifications can we prove? We're only starting to scratch the surface. And beyond spectra, okay, can we classify problems such as control? Okay, so one final thing, just to make sure you remember the message of this talk. Buzz Lightyear was right. we need to go to infinity and beyond.